Hello students, in this video I would like to discuss about depth first search. The strategy followed by depth first search is, as its name implies, to search deeper in the graph whenever possible. In depth first search, edges are explored out of the most recently discovered vertex V that still has unexplored edges, leaving it. When all the edges have been explored, the search backtracks to explore edges leaving the vertex from which was discovered. This process continues until we have discovered all the vertices that are reachable from the original source vertex. If any undiscovered vertices remain, then one of them is selected as a new source and the search is repeated from that source. This entire process is repeated until all vertices are discovered. The predecessor subgraph of a depth first search forms a depth first forest composed of several depth first trees. So the input to the depth first search is a graph which can be either directed graph or undirected graph, and the output of the depth first search is actually a depth first forest. That means it is a collection of depth first trees. So this is an introduction to the algorithm for depth first search. Vertex are colored during the search to indicate their state. There are three colors. Every vertex is initially white, grayed when it is discovered, blackened when it is finished. Finished means when all the adjacent vertices of a particular vertex is discovered, then we can blacken that. In addition to the coloring, every vertex has two timestamps. DV records when V is first discovered or when V is grayed. F of V records when search finishes examining V's adjacency list. Pi of V records predecessor or parent. Already discussed, the output of depth first search is actually a forest or a tree. So here pi of V will contain predecessor or parent, and D of V contain time at which the vertex is visited. F of V contains the search time of V's adjacency list. In our depth first search algorithm, the input will be always a adjacency list. So before going to the formal algorithm, I will try to explain depth first search with the help of the example. So here we have to find discovery time of each vertex, finishing time of each vertex, and parent of each vertex in the output depth first tree. Here's an example. First step is color all vertices to white. Here I have 6 vertices. I have colored all 6 vertices with white. Initialize pi value of all vertices as nil. Pi is the parent vertex. So here initially pi value is initialized with nil. Pi of u is nil, pi of v is nil, similarly up to pi of z is nil. Choose a starting vertex. So for depth first search we have to choose a starting vertex. We can choose any vertex as the starting vertex. Generally what we do in depth first search is we will choose the alphabetically smaller vertex as the starting vertex. So among u, v, w, x, y, z, u is the alphabetically smaller vertex, so I am choosing u. So one more thing, the data structure used in depth first search is stack. So here we chose u. So u is chosen. Color u as gray. So whenever a vertex is visited or discovered, we have to change its color to gray. So use color is changed to gray. Push u to stack. So u is pushed to stack. D of u equal to 1. That means discovery time of u is 1. Since this is the first vertex, the discovery time is 1. In next operation, discovery time becomes 2. For every operation, the time will get incremented by 1. Pi of u equal to nil, because this is the starting vertex, so parent is nil. So next step, we have to look at the top of the stack. Top of the stack contain vertex u. We have to choose a adjacent white vertex of u. So here u has two adjacent vertices, v and x. So we have to choose one of the vertex from v and x. So both v and x are white. So we have to choose either v or x. Here I am choosing v. because among V and X, V is alphabetically smaller. So V is chosen, color V as gray, V is colored as gray, push V to stack, V is pushed to stack, D of V equal to 2. Earlier the time value is 1. So the next operation, the time will get incremented by 1. So discovery time of V is 2. Pi of V is U, because we reached V from U. We reached V from U. So parent of V is U. So here pi value is changed as U. Again we have to look at the adjacent vertices of V. We have only one vertex Y, which is white. So Y is adjacent white vertex. Next we choose Y, color Y as gray, Y is colored as gray, push Y to stack, D of Y equal to 3. Earlier the time value is 2. So here this is the next operation. So the time value is incremented by 1 and discovery time of Y is 3. Pi of Y equal to V, because we reached Y from V. Here also pi value is updated with V. Again we have to look at the top of the stack. Top of the stack contain Y. So we have to select a white adjacent vertex to Y. So Y has only one vertex, that is X, that is also white. So X is adjacent white vertex. So here I choose X, color X as gray, X is pushed to stack, D of X equal to 4, discovery time is incremented, pi of X equal to Y, because we reach X from Y. Then again we have to look at the top of the stack. Top of the stack is X. So choose a white vertex adjacent to X. So X has one adjacent vertex V, but it is already grayed. So no more white vertex. So no adjacent white vertex. So what we have to do here is we have to pop X, because earlier we didn't have any adjacent white vertex to X. Color X as black. The color becomes black when all the adjacent vertices of a particular vertex is discovered, because X has only one adjacent vertex V, which is already discovered. So we have to update f of X equal to 5. Earlier the time value was 4. So X is finished when time is 5. So f of X is filled as 5. Then again we have to examine top of the stack. Top of the stack is Y. We have to check whether Y has any white adjacent vertex. Y has only one adjacent vertex X, which is already black. So no adjacent white vertex. So what will we do? We will pop Y. So Y is popped, color Y as black, Y is colored in black, f of Y equal to 6, finishing time of Y is updated as 6. Again we have to look at the top of the stack. Top of the stack contain V. Choose a white vertex adjacent to V. V has only one adjacent vertex, that is Y, which is already in black in color. So no adjacent white vertex. So we have to pop V also. So V is popped. We change the color of V as black. F of V equal to 7. Finishing time of V is 7. Now the top of the stack is U. Choose a white vertex adjacent to U. So no more white vertex are adjacent to U. So what we have to do? We have to pop U. Color U as black. F of U equal to 8. Again time is incremented by 1. Now what is the status of stack? Stack is empty. So next step is, if any white vertices remains, choose one. So here we have two white vertices, W and Z. So which one we have to choose? We have to choose W. We can choose anyone from W and Z, but here we are following a rule such that we have to choose alphabetically smaller one. So choose W. So W is visited, color W as gray, W is colored as gray, push W to stack, W is pushed to stack. So now we have just visited W, so it is discovery time. So d of W equal 9, because time is earlier time is 8, it is incremented by 1. Pi of W equal to nil, because after visiting U, V, X and Y, we choose W as the starting vertex. So pi of W, that means parent of W, is also nil. Choose a white vertex adjacent to W. So Z is adjacent to W, that is white. So Z is adjacent white vertex. So what will we do? We will push Z. So Z is chosen. Z is colored as gray. Push Z to stack. Z is pushed to stack. Now we just visited Z, so it is discovery time. It is updated as 10. Pi of Z equal to W, because we reached Z from W, so parent of Z is W. Choose a white vertex adjacent to Z. Z didn't have any adjacent vertices, so no adjacent white vertex. So what will we do? We will pop Z. So Z is popped. Color Z as black. So when coloring black means we have to label the finishing time. So f of Z equal to 11. Then now top of the stack contain W. W didn't have any white adjacent vertex. So pop W, color W as black. So W is also finished. So update its value with 12. Now stack is empty. We have to check whether any more white vertices are remaining. So no adjacent white vertices. No more white vertices. All vertices are reset. And DFS is finished. So this is the procedure for depth first search. So whenever we are discovering or visiting a vertex, we are changing its color to gray, and also we are updating the discovery time. So when will we say a vertex is finished? So when no more adjacent white vertices are there, we will say the visiting of a particular vertex is finished. At that time we will label the finishing time and also color that particular vertex to black. So this is the output we got. First we visited U, then we visited V, that's why that edge is darkened. From V we visited Y, so that edge is darkened. From Y we visited X, so that edge is also darkened. After that we visited W, then from W we have visited Z, so that edge is darkened. So when we draw the output, we will get something like that. After U we visited V, from V we visited Y, then we visited X. After that two more unvisited vertices were there in the DFS. So we started from W. So from W we have visited Z. So here we got two trees, two depth first trees. So the two trees together we call it as a depth first forest. So next is classification of edges in depth first search. So we already draw this structure from U to V, V to Y, Y to Z, and also W to Z. I just represent this input graph in another form. The darkened black edges showing the sequence such which we visited U, V, Y, X. Then we visited W and Z. So here there is an edge from U to X. In input graph we have an edge from U to X, and also we have an edge from X to V, which I drawn as a green line, and there is an edge from W to Y, and also there is an self edge in Z. But in our depth first forest we have only these darkened black edges. So these darkened black edges are called tree edges, because it is a part of depth first tree. So tree edges are edges in depth first forest. Here these are the edges in depth first forest. So those are called tree edges. Next is back edges. Back edges are those edges U, V connecting a vertex U to an ancestor V in the depth first tree. Self loops which may occur in directed graphs are also considered to be back edges. So you just look at this tree U, V, Y, X. Actually V is an ancestor of X. V is an node V is an ancestor of X. And also there is an edge connecting from X to V. Such edges are called back edge. There is an edge from descendant to the ancestor. Such edges are called back edge. So in the input graph we have an edge like this. So that edges can be considered as back edges. Forward edges are those non-tree edges u, v connecting a vertex u to descendant v in the depth first tree. So here X is the descendant and u is the predecessor, or u is the ancestor. So here in the input graph we have an edge from u to x. So u to x. So such edges are called forward edges. One more type is there. Cross edges are all other edges that can go between vertices in same depth first tree as long as one vertex is not an ancestor of the other, or they can go between vertices in different depth first tree. So here this red line is actually a cross edge because here it is going between vertices in different depth first trees. This is one depth first tree, this one is another depth first tree. From one depth first tree an edge is going to another one, so such edges are called cross edges. So one more thing, this self edge or this loop is comes under back edge. So self loops which may occur in directed graphs are all considered to be back edges. So this is a pseudocode and analysis for depth first search. So here first line, for every vertex we are doing something. We are actually initially we are coloring every vertex to white, and also we are initially storing parent value as nil to every vertex. So we have to initialize a variable time as 0 because here we are maintaining discovery time and finishing time. So for every vertex u element of E of G, if color is white, we have to call DFS visit. So DFS visit is another sub procedure. So if a white vertex is there, we are calling DFS visit. So when we visit a white vertex, first thing we do is we change its color to gray. We will increment the time and we will record the discovery time. So now for every vertices adjacent to u, for every vertices adjacent to u, we are doing these things. If color is white, we are storing pi of v as u because after u we are visiting v. So that pi value is denoted. Then we are using a recursive call. Earlier in the example we saw how stack is used. Recursion is same as stack because recursion is implemented using stack. After recursion some two pending lines are there, 8 and 9. So these two lines will execute only in the end. So if you compare the pseudocode and our example, you can see line number 1 to 6 is actually associated along with the push operation, and line number 8 and 9 are associated along with the pop operation. So line number 8 and 9 actually comes after that recursive call, and those pending operations are actually pushed to stack. So next look at the analysis. Line number 1 to 3 and line number 5 to 7 of DFS takes time v, because here we have a for loop for each vertex u element of v of g. Time v means number of vertices. So in our example we have 6 vertices. So for 6 vertices this coloring of white and parent will be set as nil. So it will take time v. And the procedure DFS visit is called exactly once for each vertex v, since DFS visit is invoked only on white vertex. So for a particular vertex, DFS of u will be called only once because it is only applied to white vertices. Here we are testing whether the color of u is white. So if the color is u only, we are applying DFS visit. Here also if the color is v only, we are applying DFS visit. So we are visiting each vertex only once. So during an execution of DFS visit of u, the loops on line 4 to 7 is executed edge of v times. So when we are visiting a particular vertex, we are also visiting its adjacent vertices. So that's the meaning of this statement. So if we already discussed in representation of graph, the total length of these adjacent vertices are actually equal to the number of edges. So here we are visiting each and every vertices once, and when we visit each vertex, we are traversing through the adjacency list also once. So the total cost of executing line number 4 to 7 is theta of e, because it is the total length of the adjacency list. So the running time of DFS is therefore v plus e. V is the time taken to visit all the vertices. So also when we visit each vertex, we are traversing through the adjacent list also. For that, the length of adjacency list is actually equal to number of edges. So we get a running time of DFS as theta of v plus v. That's all I want to discuss in this video. Thank you.